the late 1920s, mysterious deaths began occurring inside ordinary homes. There were no signs of violence, no contaminated food, no visible threat. Yet people were dying. At the time, refrigerators had evolved beyond simple ice boxes. They relied on chemical gases for cooling. Some of these gases were highly efficient, but they were also toxic, and in certain cases, nearly odorless. If a leak occurred, it could go unnoticed. A person might inhale the gas slowly, without realizing anything was wrong. In other systems, flammable gases were used. A minor leak combined with a spark could cause an explosion. These incidents created urgency. Industry needed a safer solution, and during that search, a new material was discovered, one that would go on to shape modern manufacturing. In 1936, a young chemist was experimenting with refrigeration gases. One morning, he attempted to release gas from a pressurized cylinder. Nothing happened. The tank appeared full, but no gas escaped. When the cylinder was carefully opened, researchers found a white, waxy solid inside. Under pressure, the gas had polymerized. Its molecules had bonded into long chains, forming a completely new substance, polytetrafluoroethylene. Today, it is widely known by a trade name, Teflon. Early testing revealed unusual properties. Water would not adhere to its surface. Acids produced little to no reaction. Strong bases had minimal effect. Most solvents could not dissolve it. The explanation lies in the carbon-fluorine bond, one of the strongest single bonds in organic chemistry. This bond gives the material remarkable stability. It resists chemical attack. It tolerates high temperatures. It remains largely non-reactive. At first glance, it appeared almost ideal. During World War II, advanced industrial processes required materials that could withstand extremely corrosive environments. This polymer proved valuable. Its resistance allowed equipment to function in conditions that damaged other materials. After the war, commercial restrictions were lifted. Applications expanded rapidly. By the 1950s, the material entered household kitchens. Cookware coated with this polymer allowed food to slide off easily. Cleaning required less effort. Convenience increased. Demand grew. Soon, its use expanded far beyond frying pans. What started as a kitchen breakthrough quickly evolved into a multi-industry solution. Manufacturers realized that the same non-reactive, heat-resistant surface could solve problems across a wide range of applications. It appeared in waterproof textiles, helping repel moisture while remaining breathable. Stain-resistant carpets, designed to prevent liquids from soaking into fibers. Electrical insulation, shielding wiring from heat and chemical exposure. Industrial seals and gaskets, where corrosion resistance was essential. Medical components, including specialized tubing that required chemical stability. Its low friction reduced wear. Its durability extended product lifespans. Its resistance lowered maintenance demands. From aerospace to fashion, from automotive systems to electronics, fluoropolymer materials became part of modern infrastructure. By the late 20th century, this technology had grown into a global industry. Large-scale production required complex chemical processes. To manufacture highly stable polymers, companies sometimes used additional substances to improve consistency and control during processing. One of these substances was known as PFOA. It was not the final product, but a processing aid used under specific conditions to support manufacturing efficiency. PFOA functioned as a processing aid. It helped stabilize mixtures and distribute materials evenly during production. Like the polymer itself, PFOA contains strong carbon-fluorine bonds. Scientific research later suggested that some compounds with this structure may persist in the environment. Over time, laboratory and environmental studies began examining possible long-term effects. Some findings indicated that high levels of exposure might be associated with biological changes in controlled research settings. As data accumulated, scientific review expanded. In the 1990s, environmental concerns were raised near certain industrial locations. Legal proceedings and public records led to the examination of internal documentation. Independent scientific panels were formed to evaluate available evidence. In 2013, one such panel reported probable associations between higher exposure levels and certain health conditions, including kidney cancer, testicular cancer, thyroid disease, elevated cholesterol, pregnancy-related complications. The term probable association does not establish direct causation, but reflects evidence of a possible link based on the data reviewed at the time. Research in this area continues. In the 1990s, environmental concerns were raised near certain industrial locations. Legal proceedings and public records led to the examination of internal documentation. Independent scientific panels were formed to evaluate available evidence. In 2013, one such panel reported probable associations between higher exposure levels and certain health conditions, including kidney cancer, testicular cancer, thyroid disease, elevated cholesterol, pregnancy-related complications. The term probable association does not establish direct causation, but reflects evidence of a possible link based on the data reviewed at the time. Research in this area continues. Today, scientists use the broader term PFAS to describe a family of related chemicals. Some PFAS compounds are informally called forever chemicals because many break down very slowly in nature. Studies have detected certain PFAS compounds in wildlife, in soil and groundwater, in rainfall samples, and in human blood samples worldwide. Regulatory agencies across multiple countries are reassessing safety guidelines as scientific understanding evolves. This story began with a practical goal: to create safer cooling systems. It led to the discovery of a remarkably stable material that transformed modern industry. For decades, it was considered a technological success. But long-term environmental and health research reveals an important lesson. Even highly stable materials require continuous evaluation. Scientific knowledge changes, standards adapt, policies evolve. Innovation brings benefits. It can also introduce unforeseen challenges. Balancing technological progress with long-term public health protection remains an ongoing responsibility. This video is based on publicly available historical sources, peer-reviewed scientific research, and regulatory reports available at the time of production. It does not allege criminal wrongdoing and does not provide medical advice. Scientific understanding develops over time, and viewers are encouraged to consult official regulatory and public health sources for the most current information.
Don't forget to like the video, subscribe to our channel, and share your thoughts in the comments.